Hello, SCA2020. Our paper is a hybrid Lagrangian Eulerian collocated velocity advection and projection method for fluid simulation. Little work has been done on incompressible NPM for fluids. Some papers on this are listed here. Augmented NPM for phase change in varied materials by Stamakin et al., and incompressible material point method for free surface flow by Fan et al. Typically, MAC grids are used in these formulations, with pressure at cell centers and velocity components on cell faces. In 3D, this means variables are on 4 grids. One drawback is an inability to capture standing pool or hydrostatic equilibrium. Before we begin, here is an example of rainbow-colored smoke jets showing what our method can do. We see intricate mixing as the flows collide against the spherical boundary. In this paper, our contributions are the following. A cut cell collocated velocity B-spline mixed FEM method for a Chorin splitting discretization of the incompressible Euler equations, BSLQB, a backward Semi-Lagrangian technique designed for collocated multi-quadratic B-spline velocity interpolation that achieves second-order accuracy in space and time, and a hybrid BSLQB PolyPIC method for narrowband free surface flow simulations and concentrated detail smoke simulations. We begin with the governing equations and Chorin splitting. Chorin splitting is a projection method which we apply to the incompressible Euler equations with 2 boundary conditions, solid and free surface. As shown in the figure, we denote the domain by omega, the solid boundary by partial omega s. In this splitting, the equations are split into an advection step, where velocity is first updated to an intermediate field W under Berger's equation, and a projection step, where the field is then updated under pressure and gravitational forces, subject to the incompressibility condition del.u equals 0 in the interior of the domain. Note that the derivative in Berger's equation is the material derivative. We first focus on the time discretization and the advection under Berger's equation. For the inviscid Berger's equation, the characteristics are straight lines on which the velocity is constant. Given the velocity at time tn, one common method of finding the time tn plus 1 velocity is the Semi-Lagrangian method. Using the fact that velocities are constant along characteristics, we use the time tn velocity to go backwards along the characteristic to estimate the location of this characteristic at time tn. We then interpolate from velocities at surrounding nodes. However, this is not the actual characteristic which passes through the point, as shown in the figure below. On the left, 3 characteristics are shown in blue, green, and red. Note that green is the characteristic through node xi at time tn plus 1. In Semi-Lagrangian, on the right, using the time tn velocity u and I corresponding to red will not put us on the green characteristic at time tn, but instead on the blue characteristic, resulting in an underestimate of the velocity. A more accurate approach is BSL, or backward Semi-Lagrangian. In this approach, the implicit formula for the velocity is used in combination with a root-finding algorithm such as Newton's method to solve for the exact characteristic through xi, as shown in the middle of the figure. Hence, the problem is to find the velocity field, W, satisfying the equations on the right. Before we continue to the spatial discretization, we show a comparison of Semi-Lagrangian and backward Semi-Lagrangian in 2D. Here, we see 4 jets of smoke hitting a sphere. The parameter lambda is an interpolation parameter, which we discuss momentarily. Note that backward Semi-Lagrangian exhibits more fine-scale detail than Semi-Lagrangian for both choices of this interpolation parameter. Now for the spatial discretization. We use two grids, one for pressure and one for velocity. All components of the velocity are collocated. The pressure and velocity degrees of freedom are not collocated, however, but staggered, as shown in the figure. Pressure doffs are placed at cell vertices, while velocity doffs are placed at cell centers. The blue and green regions in the figure indicate the fluid domain and solid regions, respectively. We define the velocity field using products of one-dimensional quadratic B-splines. These B-splines are centered at velocity nodes, i.e. cell centers, and they're supported on all neighboring cells. For example, in the figure from the previous slide, the B-spline associated with the center blue node here is supported on these 9 cells. This is summarized in these equations, where, by appropriate shifts and scaling, we may write all 1D B-splines in terms of a common B-spline denoted by n hat. Here, delta x is the cell width, alpha is an index over velocity components, and I is an index over the cell centers in the domain. We make this index bold to indicate that it is a multi-index over a grid. The pressure field is defined similarly, with linear instead of quadratic B-splines. These splines are centered on the pressure nodes, and have the property that they are 1 on their corresponding node, but 0 on all the others. For both the velocity and pressure fields, we express them as a linear combination of the B-splines. Returning to our backward Semi-Lagrangian equation for the intermediate velocity field W, we replace the time Tn velocity term with our discretized velocity field to obtain this equation for W evaluated at velocity nodes xi. This is a nonlinear system, so we use Newton's method, where the initial guess is the Semi-Lagrangian solution. The velocity gradient used in the Newton system is given by the expression at the bottom. Once we have obtained the values of W on the cell centers, we need to solve for the interpolation coefficients, denoted here by W bar. The reason for this is that quadratic B-splines are not interpolatory, i.e. they do not take on the values 0 or 1 at velocity nodes. Note that this is an SPD system for the coefficients W bar. However, the coefficients obtained by solving this system sometimes produce oscillatory velocities, which are not desirable. We found that a modification of the system, shown here, stabilizes the velocities. This parameter lambda takes values between 0 and 1, and as we saw earlier in the example of 4 smoke jets, the value of lambda equals 0 is very dissipative. Now that we have our BSLQB advection, we combine it with PolyPIC, or polynomial particle in cell, to create a hybrid advection scheme. In PolyPIC, we store particles with positions x and p, and PolyPIC velocity coefficients c and p. These are used to transfer momentum from the particles to the velocity grid. For more details, see the 2017 paper by Fu et al. To advect using PolyPIC, the particles are first updated using the particle velocities, which are determined from the PolyPIC coefficients. The interpolation coefficients are then given by this expression, where nr is the number of polynomial modes SR. The numerator is the momentum that particles transfers to the grid, and the denominator is the mass that they transfer to the grid. When this denominator is larger than a given threshold tau, we use this value for W bar. Otherwise, we obtain them as before from the SPD system. This is our hybrid BSLQB/PolyPIC advection scheme. This is a simulation of 2 smoke spheres colliding against each other in 3 dimensions using our advection scheme. Note that BSLQB accurately resolves vorticial details. Here is another example, where a plume of smoke hits a sphere. 0 normal velocity boundary conditions are applied on the sphere boundary, creating intricate flow patterns. The spherical boundary is not voxelized. Our formulation of the system allows for a cut cell approach, both of which we discuss momentarily. The second part of the Chorin splitting is the pressure projection. In this step, we use the Euler momentum equation along with the incompressibility constraint del.u equals 0 to apply forces to our intermediate field W, which we obtained from BSLQB/PolyPIC advection. Applying time discretization to the left-hand side, we rewrite the equations in the form shown at the bottom. To discretize in space, we take a variational approach. We take the dot product of both sides of the momentum equation with the vector-valued test function r and integrate over the domain omega. For the pressure term, we have already integrated by parts here. Next, for the incompressibility constraint, we multiply by a scalar test function q and, again, integrate over the domain. Now, in order to satisfy the solid boundary condition, on which the normal velocity is prescribed to be a, we multiply by a scalar test function mu, and this time integrate over the boundary partial omega s. We have now accounted for all equations and boundary conditions, except for the free surface condition, where we set the pressure equal to 0. To account for this, we integrate only over the remaining boundary partial omega s in the boundary term, the weak form of the momentum equation. On this part of the boundary, we do not know what the pressure is, so we introduce a Lagrange multiplier lambda. Physically, this Lagrange multiplier represents the external pressure we must apply on partial omega s in order to satisfy the normal velocity condition u dot n equals a. As for the test functions, we will require that these integral equations hold for arbitrary r, q, and mu. We have already discussed the discretization of pressure and velocity. Using the same quadratic and linear B-splines, we discretize the test functions r, q, and mu, as well as the Lagrange multiplier lambda. Note that for mu and lambda, we use a different index b instead of c to indicate that only B-splines corresponding to boundary pressure nodes are in the linear combination. We are able to resolve a standing pool of water with this choice of discretization. The variational problem is thus projected to a finite dimensional problem, represented by a linear system for the velocity, pressure, and Lagrange multiplier degrees of freedom. Here, the vector capital UN+1 is the vector of all velocity dots. The vectors capital P and capital lambda are defined analogously. M is the mass matrix, D is the discrete divergence, and B enforces the velocity boundary conditions. A is the variational boundary condition, and W is the vector of all intermediate velocities. These matrices, as well as A, are given by these integrals. By defining a matrix G using the D and B matrices, we obtain a discrete gradient operator, which allows us to rewrite the system as an SPD system for the pressure and Lagrange multiplier degrees of freedom, followed by an update for the velocity. The downside, however, is that the matrix G transpose M inverse G is dense, because the mass matrix has a dense inverse. To resolve this, we use a lumped mass approximation for the mass matrix, which is then diagonal. We now show some more examples. As mentioned earlier, our method is able to handle interesting geometries using cut cells. Here is smoke in an irregular domain. And here is a block of water falling inside of a snow globe, with a smaller sphere inside. The globe example just now was an example of a free surface simulation using our formulation. Our formulation also allows for a narrow band free surface formulation. The fluid domain we represent with a level set, and particles are seated in a band of a given width W from the zero isocontour, as shown in the figure on the right. Particles are advected and used for the hybrid BSLQB/PolyPIC advection. The level set is also advected by interpolating its value at the previous time step using the upwind location. We demonstrate this with a 3D particle render of a drop falling into a pool. We have mentioned cut cells a few times and shown examples demonstrating their application. We do cut cells by creating a level set with values on the pressure grid. We then generate a zero ISO contour and tetrahedralize the enclosed domain using a marching cubes algorithm. Finally, we integrate over these tetrahedra and boundary triangles in the integrals defining our mass, divergence, and boundary condition matrices to achieve our cut cell formulation. We are able to evaluate these integrals exactly using Gaussian quadrature of sufficient order, as the domains are triangular and the integrands are polynomials. In this figure, we show the essential cases in 3D. The green faces are the solid boundaries, and the blue region is the intersection of the grid cell and the fluid domain, divided into tetrahedra. We now show two dam break examples. In this one, we've added whitewater effects to the render, following the 2012 paper by Imson et al. In this second one, we use the bunny as the obstacle and show a particle-based render. This time, opposing blocks of water collapse and collide. In summary, we have developed an advection and projection method capable of producing intricately detailed simulations for smoke and water. There are several key limitations, however. First, our method is quite different from most standard fluid solvers used in graphics. BSLQB/PolyPIC can be used with a MAC grid, but this would require multiple solves for velocity, one for each velocity component on the different faces. Also, the stencil of our pressure system is quite wide, with 343 entries per row in 3D. In addition, the mass lumping scheme which we used to obtain a sparse system has been shown by Botella to decrease accuracy. For future work, we would like to do the following. First, use a sparse approximation to the inverse of the mass matrix without degrading accuracy. Also, while the solid boundary in our formulation is allowed to be cut cell, the free surface boundary is still voxelized. In the future, we would like to replace this with a cut cell boundary as well.